right, investigation 7.2. We are back at the side angle like we used to do, just because the track's long and I think it provides a good view. Front page of this gives you instructions for how to set up the string, the spring in the car to make sure that you're able to use the force scale, this guy here, to read out the forces when you input it. This will be useful for the lab going forward. This lab actually does a great job of connecting a lot of the topics students have been talking about. So go from work, energy, and speed equations. I think it's really, really a good lab. So what you want to do is your car is going to be facing into the rubber band. So the point that sticks out will go towards the rubber band just so you can have a consistent distance to the plunger. So go ahead and thread the string through there and pull it all the way through. It is easier to go through the top than the other way around. Oh, don't lose them. You could tie a knot up here at the top. I just went ahead and grabbed one of the string plunger clamps, and I'm just going to use that guy to hold him in. I tested it and it stays pretty well. So now my guy is stuck there and it's not going to move. Your other end of the string, you're going to go under your band. There's a little hole, and it's pictured on the document, but you're going to go under here and underneath this. Just keep feeding it through, and then you'll be able to grab it and pull it all the way through. And I'll probably cut away to the video I did on the other lab showing how to tie a knot using the string on this side, so that way you can hook up your force scale to it and get some readings. Okay, first scale will be hooked up there, and this is the setup for the first part of the lab. You'll start off by having your plunger set back 1 centimeter behind the rubber band. You can either do this using, I think the meter stick is a bit big. You could use a smaller metric ruler, or I'm just using the lines here on the track, and so I moved it back about 1 centimeter. Whatever you think is most consistent to get your measurements. But now I can carefully pull back on the car, and the trick that you want to make sure you tell your kids is don't keep pulling, because you could get any number of values. What I'm going to do is I'm going to pull until my car just hits that plunger. So you want one kid monitoring that while the other person reads out. So I'm at like 0.5 newtons if I'm accurate, just to get to there. And the students will document that on the chart. So they'll do this for 1 centimeter, they'll pull this back, do 2 centimeters, 3, 4, and 5, and get what is the force required to pull it back that far. And then they'll create a graph. Have them create a line graph, because that's going to be useful for the next part, or at least do the dots and they can connect the line. And then they can define work. The next question, here I'll show it on the camera. This is actually kind of really cool, because it's trying to help the kids see that if you got your graph for your force and distance, and this is how they should set up the graph for the previous page, so the amount of force on the y-axis, your distance on the x-axis. If you actually try to average out what the area is beneath it, that gives you your work. And this is a really cool concept, because this is like the groundwork for calculus and calc-based physics. Your students won't know that, but that's essentially what you do in calculus-based physics. So this only gives them an example up to 3 data points. They'll have it for 5, and they can use that area under the graph to give them their work for each amount. And so then they could just add up all those rectangles to get the total work done. I think that was a pretty cool idea. Gauge your students, gauge yourself on how well you think that's going to work, but that's a really cool way to get the total work done for this lab. And then they can do the work versus distance graph. The last part of the lab is pretty cool, because it connects back to some old things. They're going to be making a prediction about, okay, if we put this much work into it, what should my velocity of my car be when I let go? And they'll do that by, actually there's a really good equation for it, but they've calculated the deflection, they can measure the mass, and then they'll have the work amount from the previous graph, and so they can make a predicted speed. That is actually going to be, let's see here, I think I skipped the question. Yeah, here we are. Derive an equation for a formula of the speed of the car by the work done by the rubber band. I'm going to do a cutaway right now to show you guys what that equation looks like, because it might be a bit too much for them to come up on the. All right, this is to show you guys what is called the work energy theorem, and yet we are going in purple. So this is an equation that connects work to energy. I'm putting down the name just so if this video is not the best, you can always go somewhere else. So we're connecting work. All that is just your change in energy. In this lab, we only are dealing with kinetic energy, but normally you would do plus the change of potential and all the other types, but this is the only one that we have. Well, we know that change in kinetic energy is your final energy minus your initial energy. So your initial would be 1/2 times the mass times your initial velocity, final velocity, plus minus, I know what I'm doing here, 1/2 times the mass times your initial velocity. Now, what's nice about this equation, first it looks complex. 1/2 mv squared. Should have prepared for this a bit more. But your initial velocity, you're not starting with any. So initial velocity is 0. So all of this right here gets crossed out because that's all multiplied equals 0. So really we're just focused on this part here. And I believe that we calculated the work in the previous part, but students will know, okay, well that's my force times distance. So you can either write it out or students will have calculated. I think by this point in the lab they would know what the work is for however far back they pull the rubber band. So I'm going to keep it as W. So we have W equals 1/2 mass, which students will measure using the scale, times velocity final squared, and that's actually what we're looking for. This is our predicted velocity. So to solve for this, we're going to multiply by 2 to get rid of this half and divide by m. So we actually get 2 times the work divided by the mass equals my final velocity squared. To get rid of that square, we're going to square root both sides. So your final answer will be the square root of 2 times your work over your mass equals my final velocity. So it's just a matter of plugging things into your calculator, but you'll get a value that hopefully when they measure it using the Photogate and calculating the speed should get close to that value there. All right, thank you. All right, you should be back from that video. Now they have an equation to make a prediction. So they'll have their predicted speed. Let's say that we pulled this back to 5 centimeters. So they say, okay, if we're pulled back 5 centimeters, that means that this much work is going into this car. And if I know my mass of my car, then I'll be able to predict the speed. And so I'll just pull this plunger back a little bit. For this part of the lab, you don't want the string attached or it will mess up your data that you're collecting. I'll go ahead and hook this guy in. You'll go to CPO timer mode. Let's get this guy. And this might be a callback to some of the older stuff students have done, but it's a good review. And so they've made their prediction. They can launch it now. That set it off. You guys see the data here. I can take my time. Remember, it's 1 centimeter divided by that time gives me my speed. So they can compare their predicted speed versus their actual speed for the different rubber band deflections and see how accurate that conversion is. And hopefully, if everything's done correctly, that'll come out pretty accurate. So a few more questions after that, but if you're looking for a high-level lab that connects all that you've been learning, this one might be a little bit more hands-on, helping the students work through this, but certainly some pretty cool predictions and outcomes. All right, that is investigation 7.2.